As we talked about in class, one of our main jobs in physics is finding patterns in data that we can map to mathematical models with predictive ability. The simplest case that we have is data that fits a straight line. To fit such data by hand, we would use a transparent ruler and draw a line that represents the best average of the data points that we have. Usually when you do that, half of your data will be above the line and half the data would be below the line. When we go to find the slope by hand, we should not use data points in our calculations unless they are directly on the line. Instead, we should use lattice points, points on the graph paper grid that happen to be on our best fit line. When drawing graphs by hand, they should be as big as possible. The bigger the area that we plot our data in, the longer we can draw our best fit line, and the more likely we will be able to find lattice points. Let's use Desmos to help us understand best fit lines. Here's a set of points that we can try to make a best fit line for. We can use the slope and intercept sliders to move the line around and try to draw the best fit. What we are trying to do is minimize the average vertical separation between the data points and the line. These vertical gaps are called residuals. We can use Desmos to actually plot the residuals. Actually, I'm plotting the absolute value of the residuals. When the residuals are as close to 0 as possible, my line is the best fit line. Here is a sample set of data that I want to fit to a mathematical model. When I plot the data, it is obviously curved. How can we deal with this curved data? Well, this data appears to be parabolic. We know that in parabolas, y is proportional to x squared. If this data wants the x's to be squared, then let's do it. When I replot this data using the squared values, something really cool happens. The small x values don't change very much, but the larger values change a lot. This has the effect of stretching out the data and making it linear. We can now fit this data to a line. When we write the equation of this line, though, we need to remember that instead of x, the equation is based on x squared. This technique can work for many kinds of curves. What are the ways we can evaluate the validity of a best fit line? There are a few different ways to evaluate best fit lines. The first method is called the correlation coefficient, which is represented by the capital letter R. R is a pure number between -1 and +1 that represents how well your x and y variables are tied together based on the analysis of standard deviations. A coefficient of +1 means that there is a perfect positive correlation between the two variables. A 0 means there's no correlation. The relationship between x and y is random. A -1 means that there is a perfect negative correlation between x and y. As an alternative, you can talk about the coefficient of determination, which is the square of the correlation coefficient and is represented by the symbol r squared. R squared is a pure number between 0 and 1. It is usually interpreted as a percentage that represents how well the math model explains the variation in your data set. The closer r squared is to 1, the better the model explains the data. Another method is the mean absolute error, or MAE. In this method, you average the absolute values of all the residuals for your data points. These errors are expressed in units associated with the y-axis. The ideal MAE for a mathematical model would be 0. The larger the MAE is, the worse your fit is. Lastly, you can use the method called root mean square error, usually written as RSME. In this technique, you square the residuals, average them, and then take the square root. The RMSE comes out in terms of the units on the y-axis, and again, the best fits would have root mean square error values close to 0. Large root mean square error values indicate bad fits. R and R squared are usually only applied to linear fits. Mean absolute error and root mean square error can be applied to any type of function. Different disciplines use different techniques as their standard means of fit validation. Most data analysis software gives you options on what techniques you wish to use. LoggerPro is a program that is designed to model physical data. When we plot data in LoggerPro, we can choose from a wide range of mathematical models. I'm going to put some simple values in the data table that will generate a perfect straight line. If we go to the Analyze tab and choose Linear Fit, we are given the equation of the line as well as two metrics to help us evaluate the fit. We get a correlation coefficient R and a root mean square error value. In this case, since I drew a perfect data set on purpose, we get an R value of 1 and a root mean square error value of 0. If I tweak the data a little bit to wreck the fit, you can see that R comes down and RMSE goes up. If I mess with the data some more, I can wreck the fit substantially enough that I might want to try a different type of function. Let's try quadratic fit. That's better. When you're trying to fit complex data, you should try a couple different fits and note the root mean square error values for each one to help you make a decision on which one to use.